All right, folks, getting started here in Chapter 7. We're going to first look at how to determine the average value of a function, and then how to use the definite integral in finance. So the objectives we're going to look at in this section are Objective 1, how to determine an average value. Objective 2, apply an average value to a bank account. Objective 3, determine the total income from an income stream. And then Objective 4, determine the future value of an annuity. So you may remember that the average or mean of n numbers is the sum of those n numbers. It's supposed to say divided by n. A little typo there. In other words, you know, if I want to determine the average or the mean for a test, and there are 14 of you in the class, I would add up the scores and then divide by 14. You all know how to get an average or a mean. Well, the average value of a continuous function f on the interval ab is given by, well, it's given by that. 1 over b minus a, the integral a to b f of x dx. So just kind of think when you integrate from a to b f of x dx, that's like the adding part. You're like adding up everything. And then what's out front, 1 over b minus a. Well, b minus a is the length of the interval. So it's kind of like you're dividing by the length of the interval. So let's see how we can do this in an example. So here's the example. You know, make sure you write it all down. It's the number of 60 kilo bags of coffee that's exported from Colombia. It can be modeled by that function. And we're going to use this model to calculate the average number of 60 kilo bags that were exported from 2004 to 2009. So this average number that we're going to compute, it's going to be the, like on an annual basis, what was the average number of 60 kilo bags that were exported. So make sure you write down this example, get it in your notes, because I'm going to head off to the chalkboard and work it out. All right, folks, here we're looking at the example. I didn't write all the words down. As I suggested to you, write it down into your notes, so hopefully you did. I just wrote down the function, and we're supposed to use this function, use this model to calculate the average number of 60 kilo bags that were exported from 2004 to 2009. So we're trying to get the average value of this function on an interval from 4 to 9, because x is the number of years since 2000. So to get the average value, it would be 1 over b minus a, so that's 1 over 9 minus 4, integrating from 4 to 9. Well, this function, and boy, it's a big long function. But there it is. So now we need to get an antiderivative. We'll do two things at once. We'll go ahead and simplify. We know 9 minus 4 is 5. So this is a 1/5. I'm going to do the term-by-term integration, so I'd have a negative 149.54 over 4, x to the 4th, plus 2689 over 3, x cubed, minus 15,769 over 2, x squared, plus 37,572x. We need to evaluate that from 4 to 9, so we need to crank that through the fundamental theorem of calculus. So there's a lot of computation for you to do here. If you do it correctly, you're going to get somewhere close to 7143, and I should have probably carried it out a couple more decimal places, but I rounded it at 0.35. So what's the average number of 60 kilo bags that were exported from 2004 to 2009? Well, keep in mind in the problem it said this number is in thousands. So this is in thousands. So I would, move the decimal place to the right 3. So on an annual basis, from 2004 to 2009, annually, the average number of 60 kilo bags of coffee exported from Colombia is about 7,143,350 of those 60 kilo bags. So to make sure that you understand how to be computing an average value, like in an applied setting, I would like you now in section 7.1 to try number 26, just part B. So 26 part B. So pause the video, do number 26 part B in section 7.1. After you've done that, restart the video and I'll be at the board here working it out. Alright folks, 26 part B, there were a lot of words there, so hopefully you have the book in front of you. I'm not going to read all the words. I just wrote down what the function was, P of T. T represented the time in hours since the administration of the medication. And P of T is the percent concentration. So you were asked to find the average percent concentration on the interval 10 to 20. So that interval 10 to 20, that would be T values 10 to 20. So we're trying to find the average percent concentration from 10 to 20 hours after the administration of this medication. So in any event, we're trying to get an average value on the interval 10 to 20. So we need to do 1 over 20 minus 10, integrate from 10 to 20, 300t over 6t squared plus 5 dt. So, well, this is 1/10. So let me just kind of take care of that real quick. And what it looks like to me, well, it looks like this is just an old case of doing a u substitution. So I let u equal the denominator. Derivative, so du is a 12t dt. And, well, let's see. When I substitute in, my denominator is the u. Okay, I still need to take care of the 30t dt. So 30t dt, my du is a 12t dt. Is that a 25? Is 25 times 12? No. You know what? Let me grab my calculator real quick. Rather than trying to do this in my head, let's see. It is 25. Well, you know what? It's not too bad without having any coffee. So if du is 12t dt, 25 du is 300t dt. So I just massaged it by multiplying both sides by 25. So I'm going to put 25, I'm going to substitute 25 du in for the 300t dt. So here goes 25 du. And you know that 25 I can take and I can rip it out front of the integral sign. So I'm going to do that. See, 1/10 times 25, that's a 2.5. So let me just pull the problem right here. And now the antiderivative of 1 over u. Well, you know what that is. You know the antiderivative of 1 over u is the natural log absolute value of u. Resubstitute. See, u is 6t squared plus 5. And well, now I need to evaluate that from 0 to 20. So before I go any further, remember when we are, oops, I should get rid of those. When we are evaluating a definite integral and doing a u sub, there were 2 routes to go. So I did route 1, where I substituted and I kept off the limits of integration. Got my antiderivative, resubstituted, and now I'm going to use these original limits. Keep in mind what route 2 would be. Route 2 would be to turn these t limits into u limits. Both ways give you the same result, the exact same answer. It doesn't matter which way you take it. But in any event, when you evaluate this, and I would crank it through a calculator, you're going to end up with something pretty close to a 3.45%. So that's the average, let's see, on the interval 10 to 20, that's the average percent concentration on the interval 10 to 20. So 10 to 20 hours after the medicine was administered, the average percent concentration was 3.45%. I believe part A, you were asked to find it on the interval 0 to 10. And I would speculate that on the interval 0 to 10, you're going to have a number that's larger than 3.45% because it's the first 10 hours after the medicine was administered. But that's it for 26B. Hopefully you were able to get this done correctly. Let's head on back to the slides and see what's next. All right, after doing that example and number 26, hopefully you're seeing how to do the basics of computing an average value. Next up, we're just a quick reminder of your continuous compound interest formula. You know that if the continuous compound interest formula, you have a principal of P dollars invested into an account that earns an annual interest rate R, and remember that rate's always in decimal form, compounded continuously. Then the amount A in the account at the end of 10 years, or T years, is given by, there it is, A of T equals PE to the RT. Remember, P is also known as the present value. A is also known as the future value. So we're going to take a look at this example. Fred puts $2,800 into an account that's earning 2.75% interest compounded continuously. We're going to determine Fred's average balance to the nearest cent over the first 2 years of the account. So make sure you have this written down in your notes because it's time to head off to the chalkboard and work it out. All right, folks, in this example, remember Fred was putting $2,800 into an account, earning 2.75% interest compounded continuously. And we want to find the average value, or we want to find Fred's average balance over the first 2 years in the account. So the first thing I did was write down the compound interest function. So that's the principal, there's the rate. So we want to get his average balance over the first 2 years of the account. Well, that's basically it's finding the average value of the function on the interval 0 to 2. So it's 1 over 2 minus 0. Integrate from 0 to 2. 2,800 e to the 0.0275t dt. And let's see, we know this is 1/2. And so I have a 1/2. Let me write that down. 1/2. The integral 0 to 2. 2,800 e to the 0.0275t dt. And, well, I could rip the 2,800 out front as well. So if I rip the 2800 out front, I would have 1/2 of 2800. So that's 1400. Integral 0 to 2. And remember how easy it was to integrate e to the 0.0275t? I mean, there was a little formula for you on how to do it. You get the antiderivative to be 1400 over 0.0275 e to the 0.0275t. You evaluate that from 0 to 2, and when you do that, you crank it through your calculator, round it to the nearest cent, you get his average balance to be $2,878.43. Pretty straightforward, but I would like you to try one here. I would like you to now try here in section 7.1, 33 A and B. So you'll see in 33A, you're getting an average balance, and then in part B, you're computing the size of a bonus. So go ahead, pause the video, try 33A and B. After you've done 33A and B, restart the video, and I'll be here at the chalkboard working it out. All right, 33, you have the book, you see all the words, etc., etc., etc. I went ahead and wrote down the continuous compound interest function. That's what it is. And let's see, we were asked to find the average balance over the first year. So what's the average balance in the account over the first year? So what we need to do is, we're finding the average value of this function, technically on the interval 0 to 1. So that would be 1 over b minus a, integrate from 0 to 1, 3,500 e to the 0.038 t dt. Well, we know 1 minus 0 is 1, 1 over 1 is 1, so we have that. And I could rip the 3,500 out front. And then it's very easy to get an antiderivative. The antiderivative, we get 3,500 over 0.038 e to the 0.038 t. And when you crank this through the fundamental theorem of calculus, rounded to the nearest cent, you get 3567. Sorry, it's hard for me to read my writing. 0.35. So over the course of 1 year, that was his average balance. So then in part B, if I remember correctly, part B says that at the end of the year, you earn a bonus. You get like a bonus check where the bonus is 0.75% of the average balance. Well, folks, this is just simple multiplication. You do 0.75% of the average balance. So 0.75%, well, that's 0.0075 of the average balance. So you take 0.0075, multiply it by 3,567.35, and you get, this is the size of the bonus check, $26.76. So hopefully after the example with Fred and number 33, A and B, you see the basics of how to apply a definite integral, doing an average value in a financial setting. So let's head back to the slides and see what's next. All right. Hopefully that made sense in computing an average balance. Continuing here in section 7.1, certain services and providers of services, like the natural gas company or the water company or the electric company, they do continuously monitor usage. On a house, you'll find meters that is continuously monitoring how much you're using. Now, you don't have someone from each company there watching those meters 24/7. But since they're continuously monitoring usage, we can think of that as being what people in finance call a continuous income stream. So in our example here, we're going to look at the rate of change of revenue in thousands of dollars per year. For a new restaurant, it's projected to be, F of t equals 212 e to the 0.018 t, where t is the time in years from when the restaurant first opened. We're going to determine the total amount generated in revenue during the first 2 years the restaurant was open. So keep in mind we have a rate of change function here. This rate of change function, is going to be correlating to what is called a continuous income stream, and we'll talk about it more here in a little bit. But we're given a rate of change in revenue. To get the total amount of revenue, that's where we're going to integrate the rate of change function. Remember, when you integrate a rate of change function, it gives you a total increase or a total decrease. But make sure you have this example written down, because I'm heading off to the chalkboard to work through it. All right, folks, in this example, the lead into this example, we started to talk about a continuous income stream. We'll talk more about that here in a little bit. But in this example, we were given the rate of change in revenue. This was the rate of change in revenue for some restaurant. T represented time and years since the restaurant first opened. And the rate of change in revenue was measured in thousands per year. We were asked to determine the total amount generated in revenue during the first 2 years the restaurant was open. So here it is, that old concept again. We have a rate of change function, and we're being asked to determine the total amount generated in revenue. When you integrate a rate of change function, it gives a total accumulation. It gives a total amount. So to get the total amount of revenue generated in the first 2 years that this restaurant was open, we need to integrate from 0 to 2 the rate of change function. This is a pretty straightforward antiderivative. We're starting to see, a lot of usage of that little rule that we saw way back in, section 6.5, that the antiderivative of this in just one step, it's 212 over 0.018 e to the 0.018 t. Evaluate that from 0 to 2. And so when I evaluate this from 0 to 2, I get 431.72441. But that's not the answer, because it was given in thousands per year. So it's this many $1,000. That's the total revenue. So I would probably write my answer for the total amount generated in revenue in the first 2 years. I would convert this to thousands, and I would just say it's $431,724.41. Integrating a rate function. Basics. Integrating a rate function. So just to practice this concept, I would like you all to try here in section 7.1, number 42. So you definitely know the drill by now. Pause the video, do number 42. Once you're done, restart the video, and I'll be here at the board working it out. All right, number 42. Again, a lot of words. You have the book in front of you. I'm not going to read. You could read it. But I believe you were given this as the rate of change function for a vending machine in a college dorm. And you were asked the total amount, generated by this vending machine over the first 3 years of operation. So because it's a rate of change function, you integrate from 0 to 3, the rate of change function. Very easy antiderivative, 2500 over 0.05 e to the 0.05t, evaluated from 0 to 3, and crank this through the calculator, fundamental theorem of calculus. Remember the 3 goes in first, minus the 0 goes in, and you get $8,091.71. And that was it to number 42. So let's head on back to the slides now and see what's next. All right, after working through that example, and hopefully you were able to do number 42, it's going to be acceptable to assume that incomes or payments are continuous, even though they may actually be periodic. For example, the gas company, their electric company, you pay that off on a month-to-month basis. You get a bill once a month. You pay it once a month. But, from the gas company or the electric company's point of view, because there's a monitor on the house, monitoring usage, it's kind of thought of as a continuous income stream. Generically, the function used to model these rates of change of deposits or payments, that function, it's going to be called a rate of flow function. And if f is a rate of flow function for a continuous income stream, then the total income produced from some time t equals a to t equals b is found by integrating from a to b f of t dt. This should make sense. This really is nothing new. If f is a rate of flow function of a continuous income stream, it's a rate function. It's a rate of change function. To get a total, or the total income, you're going to integrate that rate of flow function. So that's really nothing new. Just thought I'd call it out a little bit more definitively. Continuing on, we're now going to start talking a little bit about annuities. In short, an annuity is a sequence of equal payments made at equal time intervals. Some examples of annuities. Annuities would be car payments or house payments or deposits into a retirement account, such as an IRA, a 401k, or a 403b. The future value of the annuity includes all of the deposits plus the interest earned on the deposits. So now I'm focusing a little bit more on about the IRAs, the 401ks, 403bs, those type of retirement vehicles. And here's how we compute the future value of an annuity. A lot of words here. I'm going to read through them. If n equal payments of p dollars are deposited into an annuity at an annual interest rate r, and that r is in decimal form, then the future value s for a duration of the annuity uppercase T is given by, the future value s is approximately equal to the integral from 0 to uppercase T, p e to the r, and then quantity uppercase T minus lowercase t dt. All right, we'll do an example here to show you that it's not as bad as it looks. But I do have to point out before we look at an example, it is very, very important to keep the units of time for T, uppercase T, R, and P consistent when using the future value formula. So in other words, Uppercase T, R, and P, they have to be either all be representing, years or maybe months. You can't mix the time units. So in this example that I have here, we're going to do number 45 on page 509. So you need to get the book, you need to open it and look on page 509 at number 45. And I'm probably going to talk a little bit more about the time units, and we'll set it up two ways. And, just to make sure that the time units are consistent. But I'm going to head off to the board now and do number 45 on page 509. All right, folks, number 45. Well, I know you can read it. It's here. I just wanted to kind of read through it real quick myself. At the beginning of each month, Antonio deposits $250 into his 403B plan. It's a retirement plan, which earns 6.5% annual interest compounded continuously. Determine how much Antonio will have in his account after 25 years. Round to the nearest cent. So in leading up to this, in the last slide, I said it was very important to be consistent with units of time. Notice what's happening in this problem. At the beginning of each month, Antonio's depositing $250, but the interest rate is given as an annual interest rate, so that's yearly, and then we want to know what's in his account in 25 years. So you have months and years in the problem. So you have to be consistent. When you use this formula, 0 to uppercase T, P-E to the R, uppercase T minus little t, dt. The T, the P, and the R, they all have to be the same units of time. So if you want to go the month route, where we know P is 250, well, you are going to have to convert this uppercase T, that's the duration of the annuity. For how long? Well, it's 25 years. You can't put a 25 here. That 25 is years. The 250 is how much is going in each month. So you have to take 25 years and convert it to months. Well, 25 times 12 tells us 300 months. Okay, now the interest rate. The interest rate was 6.5%. That was an annual interest rate. We need to know what it is on a monthly basis. What's the interest rate monthly? Well, that's where you'd have to take that 0.065 and divide it by 12. That gives you the monthly rate. And then, well, we know that is 300 minus t dt. So this is the route. If you wanted to look at everything, all units, uppercase T, P, and R as being monthly. If you want to convert everything into like a yearly basis, well, you'd integrate from 0 to 25 because it's 25 years. P is going to be different now. Antonio's putting in $2,500 at the beginning of each month. So how much would that be over the course of a year? Well, you take the 250 and multiply it by 12, and that gives you 3,000. That's how much is being invested on a yearly basis. Okay, now the rate. Well, the rate's already given to us as an annual rate. It's 0.065. And then we would have, 25 minus little t dt. This is the setup if you look at the P, uppercase T, and R as being increments of months. This is what it looks like when it's increments of years. Big T, P, R, big T are years. it doesn't matter which way you do the problem. Either way, you're going to get the same answer. And either way, that answer you get is $188,234.72. So the important thing here, you have to be consistent on units of time for P, uppercase T, and R. Okay, that's it for this one, and that's it for section 7.1. So at this point, go ahead and do the exercises in section 7.1. Thanks for watching.